Look around you, or imagine the space you're in right now, lying still, breathing slowly, waiting for sleep to come. It feels like time is paused here in this quiet moment. But beyond these walls, time never stops moving forward. Out there in the vast universe, things are always changing, sometimes so slowly that entire lifetimes pass without anyone noticing. From the moment you were born, you've watched change happen in small ways. Days turn into nights, seasons shift, trees grow and shed their leaves. It's natural to think of beginnings and endings as part of life on Earth. But what about everything else? What about the universe itself? Long before humans could build telescopes or launch satellites, people looked up at the stars and wondered, will they always be there? The night sky feels eternal, a pattern that never truly changes. You might think that the universe has no end, but scientists have found that even the stars are temporary. They too are part of a bigger story that moves forward through time, toward an ending so far away that it's almost impossible to grasp. Tonight, as you lie in bed, you can hold that question gently in your mind. What does it mean for the universe to end? Does it happen in an instant, like blowing out a candle? Or is it slower, so slow that it doesn't feel like an ending at all, but more like a soft fading, stretched out over trillions of years? To understand what the end means, you have to look backward too. Everything we see now had a beginning, a moment when the universe itself came into existence. Scientists call that moment the Big Bang. It wasn't an explosion in space. It was the sudden expansion of space itself, filled with energy so intense that matter couldn't exist yet. From that beginning, everything we know, the galaxies, stars, planets, and even you, slowly took shape. When you look up at the stars, you're looking back in time. The light from some stars left them millions, even billions of years ago. By the time it reaches your eyes, the star might have changed or even died. The night sky is like a snapshot of the past, tiny points of light telling you that time flows in only one direction. That direction, forward, is what carries us toward the universe's future. But time doesn't move at the same pace for everything. Our lives are short compared to the age of a star. A tree may live for centuries, a mountain for millions of years, but stars can shine for billions. Even so, they don't shine forever. Each star's fuel runs out eventually, and what happens next depends on its size. Think of the sun. It feels constant. The same warm light that guided ancient farmers still lights your morning walks today. But scientists know it won't last forever. They can see the stages it will pass through, from a stable middle age to a slow swelling into a red giant that will someday engulf nearby planets, possibly including Earth. The sun will shed its outer layers and shrink into a white dwarf, cooling down over billions of years until it's cold and dark. Now imagine that process happening to every star in every galaxy. Some stars die in spectacular explosions, leaving behind dense remnants, neutron stars or black holes that drift quietly through space. Others fade more gently, like the sun will. Each star's death changes its corner of the cosmos, and when you add up billions upon billions of them, you can see how the universe's energy gradually spreads out and thins. It's strange to think of the universe as having a lifespan, like a living thing. but the laws of physics show us that energy spreads out over time. It doesn't vanish, but it becomes less useful for creating new structures like stars. In simple terms, the cosmos is winding down. It's not dramatic, not sudden. It's a slow drift toward cold emptiness, one star at a time. Yet, even this isn't the end of the story. Black holes, for example, are leftovers of massive stars that collapsed under their own gravity. For a long time, scientists believed that black holes would last forever, the ultimate cosmic graveyards where light and matter disappear forever. But Stephen Hawking showed that black holes slowly lose mass through a process called Hawking radiation. Over unimaginable spans of time, even these dark giants will shrink and evaporate. This paints a picture of the universe's distant future that's hard to visualize. Stars gone, planets frozen or destroyed, black holes fading into nothing. What remains is a vast expanse of space where particles drift apart endlessly, and energy is spread so thin that nothing new can happen. This scenario is called heat death. It doesn't mean the universe will burn up in flames. In fact, it's the opposite. Everything cools down until there is no usable energy left to do anything. No stars, no planets, no light. Just a silent, cold expanse. But that's only one idea. Scientists have debated other possibilities too. Maybe the universe could stop expanding and contract again, a big crunch. Or maybe it could keep expanding faster and faster until it rips apart completely, the big rip. These ideas are fascinating, but right now, the evidence points to an endless expansion, pulling everything further apart over trillions upon trillions of years. When you think about an ending that slow, it doesn't feel like an ending at all. It feels like time itself is stretching so far that it loses its meaning. There will be no final moment when someone flips a switch and the universe goes dark. Instead, it will be a quiet fade, a soft hush as stars wink out, black holes disappear, and the last bits of usable energy spread too thin to do anything. For now, you are here, on a small planet, orbiting a middle-aged star that still has billions of good years left. You have warm sunlight, seasons, oceans, and air to breathe. You have a sky full of stars, each one a reminder that while endings are inevitable, they are also unimaginably far away. So as you lie in bed, you can hold that question gently in your mind. What does it mean for the universe to end? Maybe it means nothing more than change happening on a scale so vast that it's comforting to know it won't come in your lifetime, or in the lifetimes of countless generations ahead. Some people find this idea unsettling, the thought that everything we know will someday be gone. But you can also see it as part of a larger story. The same laws that guide the universe toward its distant end are the ones that made it possible for you to exist now. The same rules that will lead to the slow fade of the stars gave rise to the atoms in your body, the heat of the sun, the light that reaches your eyes each night when you look up. And so the question at the end of time is really just a gentle reminder of how precious your moment is right now. A warm bed, the steady beat of your heart, and the comfort of knowing that you are part of this universe, for now, exactly as you are. To really understand how the universe could end, you have to look back to where it all began. Everything you see around you, the earth beneath your feet, the stars you look up at, the distant galaxies we can barely detect. All of it started from a single point, or more accurately, from a tiny, dense, unimaginably hot state. This moment is what scientists call the Big Bang. It didn't happen in space. It was the moment when space itself began to expand. Before that, there was no space, no time, no matter, at least not in any way we can measure or understand. It's one of those ideas that sounds simple at first, but grows stranger the more you think about it. The Big Bang wasn't an explosion in the way we normally picture explosions, with bits flying outward through empty air. Instead, it was space itself stretching, carrying energy with it. In the first moments, the universe was too hot and dense for atoms to exist. Particles bounced around in a glowing soup of energy, colliding and transforming so rapidly that you wouldn't recognize any piece of it as something familiar today. Within fractions of a second, the universe expanded faster than the speed of light, not because anything moved through space faster than light, but because space itself grew. This early period, called cosmic inflation, explains why the universe looks so smooth and uniform on large scales. It ironed out wrinkles, spread tiny fluctuations across vast distances, and set the stage for everything that would follow. After that brief inflation, the universe kept expanding, but more slowly. It also cooled down, like hot soup left on the counter. As it cooled, particles combined to form simple atoms, mostly hydrogen and helium. Light, which had been bouncing endlessly from particle to particle, could finally travel freely. This ancient light, the cosmic microwave background, is still out there, a faint echo of that early moment. Scientists can measure it with radio telescopes, capturing the universe's baby picture. Over millions of years, slight differences in the density of matter led to clumps forming. Gravity pulled gas together, creating the first stars and galaxies. The light from these first stars relit the universe, turning it from darkness into a place where energy could concentrate and shine. Every galaxy you see through a telescope is part of this same history. Each one is a collection of matter shaped by gravity, following the same laws that emerged in those first moments. Stars burn by fusing hydrogen into helium, just as they have since the first stars were born. Some of that hydrogen came directly from the Big Bang, the universe's original raw material, recycled again and again. It's strange to think that the atoms in your body were part of that story, too. The hydrogen in the water you drink was forged in the first few minutes after the Big Bang. The carbon, nitrogen, oxygen, and other elements came later, formed in the cores of massive stars that lived and died long before our sun was born. Those stars exploded, scattering their enriched guts across space, seeding new clouds of gas that would one day form planets, oceans, and living things. All of this happened because of expansion. If the universe had stopped expanding early on, gravity would have pulled everything back together into a hot, dense state, possibly triggering another Big Bang in a cycle of endless bounces. But that's not what the evidence shows. Observations of distant galaxies, first by Edwin Hubble in the 1920s and then refined by generations of astronomers, confirmed that galaxies are moving away from each other. Space itself is stretching, and that expansion isn't slowing down. It's speeding up. This accelerating expansion is driven by something scientists call dark energy. a force or property of space that we don't fully understand yet. Unlike gravity, which pulls matter together, dark energy pushes space apart. It makes up about 68% of the universe's total energy content, yet its true nature remains one of physics' biggest puzzles. It's invisible. It doesn't clump like matter does, and it seems to be constant, or close to it. So when you hear that the universe will end, it really means that this expansion will go on forever. Galaxies will drift apart until they're too far to see. Over tens of billions of years, the sky above Earth will look emptier and emptier. New stars will stop forming because the gas clouds that fuel them will get used up or scattered. Existing stars will burn out, leaving behind cold remnants like white dwarfs, neutron stars, and black holes. In the far future, the expansion means that light itself will stretch. The wavelengths will get longer and longer, shifting out of the visible spectrum until any remaining warmth is too faint to detect. Even if you could live that long, you wouldn't see the beautiful, crowded night sky you know today. It would be black and quiet, with only a few dying sparks of light. This knowledge comes from decades of careful measurement and observation. Scientists look at distant supernovae, exploding stars that act as cosmic mile markers, to measure how fast galaxies move away. They map the cosmic microwave background to see the fingerprints of the universe's first moments. They use giant telescopes to study how galaxies cluster together, revealing the invisible scaffolding of dark matter that holds them in place. All these clues point to the same general outline. The universe began in a hot, dense state. It expanded and cooled. It grew stars and galaxies, and it will continue expanding, likely forever. Some details remain uncertain. How dark energy works, whether it changes over time, whether other forces might counteract it. But the overall picture is remarkably consistent, confirmed by multiple lines of evidence. It's natural to wonder why this matters for everyday life. For you, here and now, the end of the universe is so distant that it's easy to ignore. No one will be around when the last star flickers out or the last black hole evaporates. But thinking about these huge timescales can put things in perspective. It reminds you how brief a human life is compared to cosmic time, and how much we've learned in just a few thousand years. We started as a species that could barely guess what stars were. Now we know they have life cycles. They make the elements we depend on, and they will not shine forever. We understand that the sky we look at tonight is just one frame in a movie that has played for billions of years and will continue long after we're gone. When you lie awake, you might feel small in the face of this, but there's another way to see it. We're here to witness this moment. In all the vastness of time and space, you exist now, when the stars are still burning, the night sky still glows, and the universe still has warmth and light. Someday, it will be different, but for now, you have a front row seat to the grandest show there is. So, as you drift off, remember that the story of the universe is your story too. The same expansion that will one day spread everything thin made it possible for stars and galaxies to form, and for life to appear on a small blue planet circling an average star. From a tiny, brilliant beginning to an ending that will come so slowly you'd never feel it, you are part of the same unfolding timeline carried forward by the silent stretching of space. Once you understand that the universe has been expanding ever since the moment it began, it's natural to wonder what that really means for everything we see. It's one thing to say that space is growing. It's another to think about how that slow stretching shapes the fate of every star, galaxy, and piece of matter drifting through the cosmos. The expansion was first measured in the early 20th century when astronomers like Edwin Hubble noticed that distant galaxies weren't just sitting still. By studying the light they emitted, they found that the light was shifted toward the red end of the spectrum, a clue that these galaxies were moving away from us. The farther away a galaxy is, the faster it appears to be receding. This wasn't because the galaxies were flying through space on their own, but because space itself was expanding, carrying them along like raisins in a rising loaf of bread. At first, people thought this expansion might slow down over time. After all, galaxies contain huge amounts of mass. Gravity pulls mass together. So it made sense to think that the combined pull of everything in the universe would eventually counteract the expansion, maybe even cause it to stop and reverse one day. For decades, scientists debated whether the universe would expand forever or collapse in a big crunch. But when better telescopes and more detailed surveys became possible in the late 20th century, something unexpected showed up. In the 1990s, two separate teams of astronomers studied distant supernovae, exploding stars that shine so brightly they can be seen billions of light years away. By measuring how far away these supernovae were and how much their light had stretched, the teams discovered that the expansion of the universe isn't slowing down at all. It's speeding up. This discovery changed everything. Suddenly, the question wasn't whether the universe would stop expanding, but what it means to live in a universe that grows faster with time. The force driving this acceleration is what scientists call dark energy, a mysterious property of space itself that seems to push galaxies apart. Dark energy is still not fully understood. It doesn't behave like ordinary matter, and you can't see it directly. But its effects show up in how galaxies move and how the large-scale structure of the universe looks today. As the universe expands faster and faster, galaxies move away from each other at increasing speeds. Over time, this has dramatic consequences. Right now, when you look up at the night sky, you see the Milky Way's stars and, if you have a telescope, the fuzzy shapes of distant galaxies. But billions of years from now, future astronomers, if there are any, will see fewer and fewer galaxies. The expansion will push distant galaxies so far away that their light can no longer reach us. The night sky will grow emptier, not because stars have disappeared, but because they're drifting beyond the cosmic horizon, the limit of what light can travel to reach us. This slow isolation has already begun. Our Milky Way galaxy is part of a small cluster called the Local Group, which includes Andromeda and a few dozen smaller galaxies. Gravity keeps the Local Group bound together, stronger than the force of expansion at these small scales. In a few billion years, the Milky Way and Andromeda will merge into a single, massive, elliptical galaxy. From that point on, our local stars will stay together, but everything beyond the Local Group will continue to drift away. Imagine what that means. One day, far in the future, the night sky could be almost empty. The light from galaxies that now shine in our telescopes will be gone, stretched so much that it fades to darkness. Our cosmic neighborhood will feel like a lonely island, surrounded by a vast ocean of empty space. This future is tied to a principle called the cosmic horizon. Because light travels at a finite speed, there's a limit to how much of the universe we can see. Right now, we can detect light that's traveled for more than 13 billion years, letting us glimpse ancient galaxies near the edge of the observable universe. But as expansion accelerates, more and more of that distant light will slip out of reach, pulled away faster than it can travel toward us. Eventually, only our merged local group will remain visible. Everything else will fade behind an invisible boundary we can never cross. It's not that the galaxies vanish, they just become unreachable. The cosmic horizon expands away from us, carrying the rest of the universe beyond our sight forever. This might sound bleak, but it's also a reminder of how deeply connected everything once was. The universe's earliest light, the cosmic microwave background, shows us that everything we see today started in the same dense, hot state. The matter that makes up your body, the Earth, the Sun, and all the stars began in that same cosmic soup. Over billions of years, it spread out, gathered into galaxies, and formed the structures that fill our night sky. But the expansion guarantees that the visible links between these structures won't last forever. The expansion also affects how matter behaves at the largest scales. Galaxies not bound by gravity will move apart endlessly. Gas clouds will drift away from each other. Once stars burn through their fuel, there will be no new gas to make new ones. Star formation will slow down, then stop altogether. The bright, star-filled galaxies we see now will grow old and fade as their last suns flicker out. In this distant future, the universe enters what some scientists call the degenerate era. This is when normal stars have died, leaving behind white dwarfs, neutron stars, and black holes. Planets will either be destroyed by dying stars or set adrift in the darkness. Only these cold remnants will remain, drifting silently in the darkness, moving further apart as space continues to stretch. If you could jump billions of years forward, you wouldn't find the universe recognizable. No brilliant spiral galaxies, no glowing clouds of gas where new stars are born. Just scattered embers, dense, dim objects moving through an ever colder void. It can feel strange to think about an ending that's not really an ending in the way you're used to. On Earth, an ending often means something sudden. A storm blows through, a candle burns out, a life comes to a close. But the end of the universe's visible connections is slow and quiet, more like a candle that burns down over billions of years until all that's left is cold wax and darkness. Some scientists find comfort in this. The same laws of physics that predict this slow fade are the laws that let stars shine in the first place. Expansion gave us the galaxies, the stars, and the tiny particles that became the building blocks for everything we know. Without expansion, there would be no sky full of stars to wonder about. It's worth remembering that the expansion doesn't erase what exists within your reach. Here in our little corner of space, the sun still burns bright, and the Milky Way's stars still shine. Gravity keeps them bound together, resisting the pull of expansion on the grandest scales. The stars in our local group will stay neighbors for as long as they last. So as you lie in bed, think of this quiet drift. The universe is stretching all the time, but it's not in a hurry. It has been expanding for over 13 billion years, and it will keep expanding for trillions more. There's no sudden rush, no single moment when everything ends, just a steady, silent drift outward, galaxies like lanterns floating further and further apart on a dark, endless sea. And here you are, in the brief span when the night sky is still full of light. A perfect time to look up, wonder about what came before, and imagine the vast, slow journey yet to come. As the universe expands and galaxies drift ever farther apart, the real engines of cosmic change keep working inside those galaxies for billions of years. These engines are stars, the tiny, steady fires that build and transform everything we know. Understanding how stars live and die is at the heart of understanding how the universe will eventually fade away. It's easy to take stars for granted. The sun rises every day, warming the planet and lighting up our skies. But each star is a delicate balance of forces that took millions of years to ignite. The simplest way to picture a star's life is as a long battle between gravity and pressure. When a cloud of gas and dust gathers in space, gravity starts pulling it inward. The particles collide more and more often, heating up as they squeeze tighter. When the core gets hot enough, millions of degrees, nuclear fusion begins. Hydrogen atoms fuse together to form helium, releasing energy that pushes outward, counteracting the inward pull of gravity. This balance holds a star together for most of its life. The larger the star, the hotter and brighter it burns, but also the faster it burns through its fuel. A star like our Sun lives a stable life for about 10 billion years. More massive stars might burn out in only a few million years, while the smallest red dwarfs can glow gently for trillions of years, far longer than the universe has existed so far. Fusion inside stars does more than create light and heat. It's also how the universe manufactures the elements that make up everything else. The carbon in your body, the oxygen you breathe, the calcium in your bones, all were forged in the cores of long-dead stars. When these stars reach the end of their fuel supply, they die. But their death is often what spreads those elements into space. Stars like our Sun swell into red giants when they run out of hydrogen in their cores. Their outer layers expand and cool, drifting away into space and forming beautiful, ghostly shells of gas called planetary nebula. What remains behind is the core, a dense, hot ember called a white dwarf, about the size of Earth, but with the mass of the Sun. Over trillions of years, these white dwarfs will radiate away their leftover heat and become cold, dark objects known as black dwarfs. Theoretical, because the universe isn't old enough for any to exist yet. More massive stars end with more drama. When a star many times larger than the Sun runs out of fuel, its core collapses in an instant, triggering a supernova, an explosion so bright it can outshine an entire galaxy for a short time. These explosions scatter heavy elements far and wide, seeding new star systems and planets. The leftover core becomes either a neutron star, an incredibly dense ball about the size of a city, or, if massive enough, a black hole. This cycle, star birth, life, and death, has shaped the universe for billions of years. But it can't go on forever. Star formation depends on giant clouds of gas gathering and collapsing. As time passes, much of this gas gets locked away inside stars and remnants. Galaxies use up their raw material. New stars still form today, but the rate is slowing down, and in the very distant future, the last new stars will be born. Astronomers estimate that in about 100 trillion years, star formation will essentially stop. By then, the only shining stars will be the smallest red dwarfs, the slowest burners. As they finally fade, the universe will enter what scientists call the degenerate era, a time when the cosmos will be lit only by the cooling embers of white dwarfs, the dense neutron stars left behind by ancient supernovae, and the black holes formed from the biggest collapses. These leftovers might sound lifeless, but they're fascinating in their own right. A white dwarf is so dense that a teaspoon of its material would weigh several tons. A neutron star is denser still. A single teaspoon would weigh 1 billion tons. Black holes, for their part, are even stranger. Regions where gravity is so strong that nothing, not even light, can escape. They will become the universe's last major structures. During this degenerate era, the universe will look very different from the one you see now. The bright spiral galaxies with their glowing arms will be gone. There will be no nebulae painting the sky with color. No new stars will flicker into existence. Everything will grow dimmer and colder as the last pockets of warmth spread thin. Gravity will keep some of these remnants together. Small groups of white dwarfs or neutron stars might drift through space in loose clusters, sometimes colliding and merging. When they do, they can release brief flashes of energy, but these events will become rarer as the distances between objects grow. The universe's expansion will keep pulling everything apart on the grandest scales. In this distant future, the cosmic background radiation, the leftover glow from the Big Bang, will also fade. Right now, it's about 2.7 degrees above absolute zero. Over trillions of years, it will cool to nearly absolute zero as the universe expands. Any remaining heat will stretch into wavelengths so long they carry almost no usable energy. At these timescales, even stable objects can break down. Protons, the building blocks of atoms, might eventually decay, something predicted by some theories, but not yet observed. If they do, then over unimaginable stretches of time, matter itself will disintegrate into lighter particles, which will drift apart even more. Long after the last star flickers out, black holes will dominate the universe. They'll swallow up stray matter that comes too close. Bits of rock, cold gas, or even the last wandering remnants of dead stars. But black holes, too, are not forever. Thanks to a process called Hawking radiation, they very slowly lose energy. For large black holes, this takes far longer than the current age of the universe. A black hole with the mass of the Sun would take about 10,067 years to evaporate completely, a number so vast it barely means anything to the human mind. Eventually, one by one, black holes will shrink, radiate away their energy, and vanish. What remains after that is a universe that is dark, cold, and nearly empty. A handful of subatomic particles will drift endlessly through space that keeps stretching wider, carrying them apart so that they almost never meet. When you think about these timescales, it's natural to feel small. Human history is a blink compared to the lifespan of a star, and even a star's life is brief compared to the cosmic timeline that lies ahead. But these ideas don't have to make you feel lost. They can remind you that you are part of an ongoing story. The same fusion that lights the sun happens in different ways all across the universe. The warmth that reaches your face on a sunny day began as nuclear reactions in the sun's core. Reactions that are themselves part of a chain that began billions of years ago and will continue long after we're gone. So as you lie in bed, breathing slowly, you can picture this vast, patient process. Clouds of gas become stars. Stars light up planets, and the energy they release travels through space, sometimes for billions of years, before it touches your eyes. This energy is the thread that connects you to everything else, a quiet sign that, for now, the universe is still alive with light. Someday, it won't be. The story of stars will come to an end. But tonight, they're still here, burning quietly overhead, carrying the universe's long memory and reminding you that endings, when they come, can take an eternity to unfold. Among all the stars scattered through the universe, there is one that matters more to you than any other: the sun. It's an ordinary star by cosmic standards, not the biggest, brightest, or oldest. But for Earth, it's everything. Its light powers the plants that feed us, warms the oceans, drives our weather, and marks the passage of each day. Yet like all stars, the sun will not last forever. Its end is certain, written into the physics of how it shines. The sun is about halfway through its life right now. It's around 4.6 billion years old, and it has roughly another 5 billion years to go before things start to change dramatically. That might sound like forever, but in the life cycle of stars, it's just a comfortable middle age. Inside the sun, hydrogen atoms fuse together to make helium. This fusion process releases energy, the light and warmth that reaches you every day. Right now, the sun is steady and balanced. Gravity pulls inward, trying to collapse it, while the energy from fusion pushes outward, holding it up. That balance is why the sun shines so reliably. But slowly, deep in the core, the amount of hydrogen fuel is dropping. As the hydrogen runs out, the sun will adjust. It will start to fuse helium into heavier elements like carbon and oxygen, but this process isn't as efficient or stable. The balance between gravity and pressure will change, setting off a chain of events that transforms the sun from a gentle yellow star into something very different. When the hydrogen in the core is nearly gone, the core will contract under gravity. As it shrinks, it heats up, and the outer layers of the sun will expand dramatically. Over millions of years, the sun will grow into what scientists call a red giant. This transformation is hard to picture from here on Earth. The red giant sun will be so huge that its outer layers could reach the orbit of Mercury, Venus, and possibly even Earth. Our familiar blue sky would be replaced by a vast reddish disk filling the heavens. If Earth isn't swallowed up entirely, its surface will be scorched, the oceans boiled away, the atmosphere stripped by the expanding solar winds. It sounds violent, but the process takes time. A red giant isn't an explosion, it's a slow swelling. For a star like the sun, becoming a red giant is the natural next step in its aging process. As its outer layers expand, the core continues to shrink and heat up until the helium there begins to fuse. The star becomes unstable, pulsing and shedding its outer gas layers into space. Those outer layers drift away, forming what's called a planetary nebula, a glowing shell of gas illuminated by the remaining hot core. Through telescopes, planetary nebulae look like cosmic ghosts, delicate, colorful clouds that drift through space. They don't last long, at least in astronomical terms, maybe tens of thousands of years before they fade away. At the center of this nebula sits the Sun's core, now a white dwarf. This white dwarf will be about the size of Earth, but with about half the mass of the original Sun packed inside it. No more fusion takes place in a white dwarf. It shines at first because it's incredibly hot. Temperatures can exceed 100,000 degrees Kelvin, but it has no new source of energy. Over time, it cools, radiating its leftover heat into space. In our current universe, white dwarfs are still quite young in cosmic terms. None has yet had time to cool completely. But given enough time, trillions of years, these white dwarfs will fade into darkness. They will become what physicists call black dwarfs. Cold, dark cinders drifting silently through space. It's strange to imagine that this is the fate of our Sun, the warm, life-giving star reduced to a dark, frozen relic. But this fate is not unique. About 97% of the stars in our galaxy will end their lives this way, gently leaving behind white dwarfs that cool and dim until they're invisible. What happens to Earth? Long before the Sun reaches its red giant phase, life here will have become impossible. As the Sun grows older, it gradually becomes brighter. Even now, it shines about 30% brighter than it did when life first appeared on Earth. In the next billion years, that brightness will increase enough to make Earth's surface too hot for complex life. The oceans will evaporate, and the atmosphere will change dramatically. By the time the Sun swells into a red giant, Earth may already be lifeless, or it may have been swallowed up entirely, its matter added to the Sun's outer layers. If it survives, it will be a scorched, airless rock orbiting a dying star. This is not something to fear. It's so far in the future that it doesn't affect our lives in any practical way. Instead, it's a reminder that even the most stable things we rely on, the Sun's warmth, the cycle of days and nights, are part of a larger process that moves at its own pace. In a sense, the Sun's future gives us perspective on the long timeline of the universe. Our star is just one of billions. Each one is a brief flare of order and warmth in the darkness, turning simple hydrogen into the building blocks of planets and life. When its time comes, the Sun will return its material to space, enriching the cosmic environment for the next generation of stars and planets. You can see this story written across the Milky Way. When you look up at the night sky and see nebulae, those colorful clouds, you're seeing the remnants of ancient stars that once shone like our Sun. Those clouds are full of gas and dust that will collapse to make new stars, new planets, and maybe even new life. When you understand the life cycle of the Sun, you can see how it fits into the bigger picture of the universe's future. The Sun's gentle fading is part of the gradual process that will lead to a dark, quiet cosmos. Every star that dies and leaves behind a white dwarf or black hole is another step toward the day when the universe's energy is spread thin, when no new stars can form, and when all that remains are cold remnants drifting apart in endless night. But for now, the sun still shines. It has billions of years left to burn bright, to warm our planet, to light up the days and feed the plants that keep us alive. That warmth reaches you every morning, a reminder that in a universe where everything changes, some things remain steady for a very long time. So as you lie here, you can hold this simple truth in your mind. Endings are part of the story, but they unfold on scales so vast they feel almost eternal. You are here, in the bright middle of the sun's life, with starlight on your face and countless days ahead. There will be time enough to wonder what comes next, but tonight you can rest knowing that for now, the light keeps shining. When the sun finally sheds its last layers and leaves behind a white dwarf, it will join an enormous population of other dying stars that meet the same quiet fate. White dwarfs are the cosmic embers that glow faintly long after the fires of fusion have gone out. They mark the slow cooling of the universe, tiny reminders that even in deep time, change doesn't stop, it just slows down. To understand why white dwarfs matter, it helps to think about what they really are. Imagine taking the entire mass of our sun, more than 330,000 times the mass of Earth, and squeezing it down until it's no bigger than our planet. A white dwarf is so dense that a single teaspoon of its matter would weigh several tons. It's made mostly of carbon and oxygen, locked together in a crystalline structure that some scientists compare to a gigantic diamond in space. This strange object doesn't generate new energy. Instead, it glows because it's still extremely hot. When a star becomes a white dwarf, its surface temperature can be more than 100,000 degrees Kelvin, far hotter than the surface of the sun is today. But without fusion in the core, there's no new heat to replace what radiates away. Over billions, trillions, and even longer stretches of time, that leftover heat seeps out into space. In the current age of the universe, white dwarfs are relatively young. The oldest ones are still warm enough to shine dimly. But given enough time, they will keep cooling until they are so cold that they no longer emit visible light. When that happens, they will become what scientists call black dwarfs, cold, dark, and almost impossible to detect. No black dwarf exists yet because the universe simply hasn't been around long enough. Even the oldest white dwarfs still glow. But physicists can predict what they will become by calculating how long it takes for a white dwarf to radiate away its remaining heat. The answer is staggering. It could take 100 trillion years or more for a white dwarf to cool to near absolute zero. Black dwarfs will be among the last visible traces of the stars that once lit up the cosmos. They will drift through the darkness, alone or in loose groups, bound by whatever gravity holds them together. Some might get knocked free by close encounters, becoming rogue travelers through empty space. Others could collide, though such collisions will become rarer as time stretches out and distances grow vast. While white dwarfs represent a gentle fading, there's another kind of leftover that tells a different story about how the universe loses its energy: black holes. Unlike white dwarfs, black holes are born from violent endings. When a massive star, many times bigger than the sun, runs out of fuel, its core collapses under gravity so intensely that it forms a point with such strong gravity that not even light can escape. These black holes can be stellar-sized, like those formed from a single star's collapse, or much larger, like the supermassive black holes that sit in the centers of galaxies. Some of these giants contain the mass of millions or even billions of suns packed into a region no bigger than our solar system. For billions of years, black holes feed on the gas, dust, and stars that come too close. They grow larger, pulling in more matter and merging with other black holes when galaxies collide. But in the far future, even these cosmic giants will face a slow, quiet end. In the 1970s, physicist Stephen Hawking showed that black holes are not entirely black. Through a quantum process called Hawking radiation, black holes can slowly lose energy by emitting particles near their event horizons, the boundary beyond which nothing can return. Over unimaginable timescales, this process will cause black holes to shrink, radiate away their mass, and eventually disappear completely. For a black hole with the mass of our Sun, this would take about a time span so long it dwarfs the current age of the universe, which is only about 13.8 billion years. The supermassive black holes at the centers of galaxies will last even longer, but they too will eventually evaporate, leaving behind nothing but faint radiation drifting through the endless dark. Together, these processes, the cooling of white dwarfs and the evaporation of black holes, mark the gradual unwinding of cosmic energy. This is the heart of what scientists call the heat death of the universe, a state where all the usable energy has spread out so evenly that nothing new can happen. No new stars can form because the raw material is gone. No leftover heat remains to build new structures. There are no more gradients for energy to flow from hot to cold. Everything has evened out forever. Some physicists describe this final state as maximum entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics says that in any closed system, entropy tends to increase. In the universe, this means that energy becomes more spread out and less available to do useful work. Over vast stretches of time, the cosmos moves toward this state naturally. It's worth pausing to realize how gentle this ending is. There is no sudden catastrophe, no cosmic explosion, no violent finale. Instead, it's more like a campfire burning down to its last glowing embers, then slowly cooling until only ashes remain. In this future, the few remaining particles, scattered protons, electrons, and faint traces of radiation, will continue to drift apart as the universe keeps expanding. They may occasionally collide, but these meetings will become so rare that, for all practical purposes, the universe will be still. Some theories suggest that protons themselves may not last forever. If protons decay, then even the most basic building blocks of matter will eventually vanish, leaving behind only light particles like photons and neutrinos. But this is still speculative. No one has observed proton decay yet, so it remains one of the many open questions about how the universe truly works. If you imagine standing in this far-off future, trillions upon trillions of years from now, you wouldn't see much at all. No stars, no planets, no glowing clouds of gas, just an endless, cold expanse where the last black dwarfs and black holes are quietly disappearing into the darkness. Yet there is something strangely comforting about the sheer scale of it. Our daily lives move quickly. Days turn into nights, weeks into months, years into decades. Compared to the lifespan of a human, a star's life seems eternal. And compared to the lifetime of white dwarfs and black holes, even stars are fleeting. It's easy to feel small in this timeline, but there's another way to look at it. You exist during a unique window when the universe is still alive with energy and light. Stars shine in every direction, planets circle their suns, and life can thrive on at least one small world that you call home. White dwarfs and black dwarfs remind us that change never really stops. It just slows down until it's almost impossible to see. Somewhere, the remnants of the stars we know today will keep drifting, silent witnesses to a universe that keeps expanding even when it seems nothing else is left. As you lie here, breathing slowly, think of those tiny points of fading light. They are what remains when all the brilliance has passed, proof that endings can take longer than anything we can imagine. And in the meantime, your place is here, in the bright age of stars, with warmth and light still all around you. For all the quiet fading that happens when stars die into white dwarfs and black dwarfs, not every star goes so gently. Some stars end their lives in ways so powerful that they reshape entire galaxies and fill the universe with the ingredients for new generations of stars and planets. These are the stars that die in explosions, leaving behind some of the strangest objects in existence. Black holes. The story of a black hole begins like any other star, with a giant cloud of gas collapsing under its own gravity until fusion ignites. But when a star is massive enough, much larger than our sun, its ending is far more dramatic. Once it burns through its hydrogen and helium, it starts fusing heavier and heavier elements. This process keeps building up new layers inside the star, like the layers of an onion, until it reaches iron in its core. Iron is the end of the line for fusion because combining iron atoms doesn't release energy, it consumes it. When fusion stops supporting the core, gravity wins. In a fraction of a second, the core collapses. The outer layers crash inward, bounce off the dense core, and explode outward as a supernova. A supernova is one of the most powerful events in the universe. For a short time, a single exploding star can outshine an entire galaxy. The explosion sends shock waves through space, stirring up gas and dust that can later form new stars and planets. In a way, a supernova is a violent but necessary part of the universe's cycle of renewal. What's left behind depends on the mass of the original star. If it's big enough, the collapsing core becomes a black hole, an object so dense that not even light can escape its gravity. At the center of a black hole is a point called a singularity, where the laws of physics as we know them break down. Surrounding it is the event horizon, the invisible boundary that marks the point of no return. Black holes come in different sizes. Stellar mass black holes are formed from individual massive stars. But there are also giants, supermassive black holes, millions or billions of times more massive than our sun. These sit at the centers of galaxies, including our own Milky Way. How they formed is still a mystery, but they've shaped the structure of galaxies by pulling in gas, stars, and sometimes other black holes. As the universe ages, black holes become its last dominant structures. When galaxies collide, their central black holes can merge, creating even larger ones. This process continues for billions of years. In the distant future, When star formation slows to a stop and the last stars burn out, black holes will remain, slowly sweeping up any stray matter that drifts too close. But even these giants are not eternal. As Stephen Hawking showed, black holes slowly lose mass through Hawking radiation. This process is so slow that it has no effect on black holes today, but over unimaginable stretches of time, even the biggest black holes will shrink and disappear. One by one, they will evaporate, releasing their last traces of energy into an ever-expanding, ever-cooling universe. It's a strange fate for something so powerful. Not a dramatic collapse, but a slow fading into nothingness. Long after the last stars have gone dark and the last white dwarfs have cooled to black, black holes will remain as the final guardians of what once was a bright, star-filled cosmos. And when they, too, are gone, what's left is an endless sea of cold, thin radiation and subatomic particles drifting apart forever. It's a vision of the universe as a place that doesn't end in fire or violence, but in a quiet, endless dispersal. Still, black holes remind us how much the universe can change and how its grandest structures emerge from the simple forces of gravity and time. They're not monsters lurking in the dark. They're a natural part of how the universe recycles itself, pulling matter in, breaking it down, and returning it to the void. As you lie here, think of these dark giants drifting silently through the darkness. They carry the memory of massive stars that once burned bright, of galaxies that once collided and danced, of a universe always in motion, even when it seems still. The story of black holes is just one more step in the slow, patient unwinding of everything, a reminder that even the strongest forces fade with enough time. Even as black holes hold the last whispers of energy, the galaxies that surround them are not frozen in place. They drift, they pull each other closer, and sometimes they merge in slow, silent collisions that can take billions of years to complete. One day, the Milky Way and Andromeda, the two largest galaxies in our local group, will meet. Right now, they're about 2.5 million light-years apart. That sounds like an impossible distance, but they're moving toward each other at about 110 kilometers per second. In about 4 billion years, they'll begin to collide. Galactic collisions aren't like car crashes. The distances between individual stars are so vast that when two galaxies merge, most stars pass by each other without ever hitting. Instead, gravity pulls the stars into new orbits, distorting the galaxies' shapes and flinging stars into long streams. Clouds of gas collide and compress, sometimes triggering bursts of new star formation. From Earth, if anyone is still here to see it, the night sky would be spectacular. The faint band of the Milky Way stretching into a sky filled with the bright core of Andromeda, growing larger every few million years. As the galaxies merge, the stars would swirl together into a new shape, likely a giant elliptical galaxy with a smooth, rounded form instead of the familiar spiral arms. At the heart of this new galaxy, the supermassive black holes of the Milky Way and Andromeda would eventually spiral together and merge. When they do, they'd release enormous amounts of energy in the form of gravitational waves, ripples in space-time that spread out across the universe. After the collision settles, the new galaxy would continue to drift through space, but its environment will have changed. Over time, the gas that fuels star formation will be used up. new stars will stop appearing. The stars that remain will burn through their fuel one by one, leaving behind white dwarfs, neutron stars, and black holes, the same fate that awaits all galaxies, whether they merge or drift alone. These galactic collisions will continue for trillions of years wherever gravity can overcome expansion. Small galaxies will keep falling into larger ones. Clusters will grow larger. But eventually, the force of expansion will win out on the biggest scales. Clusters and superclusters that aren't tightly bound will drift apart, leaving behind islands of stars and black holes separated by ever-growing oceans of empty space. In this far future, the universe will look very different from today's night sky. Right now, we see billions of galaxies scattered across space. But someday, future observers, if there are any, might see only the stars in their own merged galaxy. Everything beyond will have slipped beyond the cosmic horizon, carried away by expansion faster than light can cross the distance. It's a reminder that what feels fixed is always changing. Galaxies are not static. They are vast gatherings of stars, gas, dust, and dark matter, all moving under the pull of gravity. Their shapes shift, their stars orbit, and their fates are tied together in slow dances that can take billions of years. You can think of the Milky Way and Andromeda not as separate islands, but as travelers destined to become one. Long after their spiral arms have blended, the stars born from their collisions will shine for trillions of years before they, too, fade. And through it all, the universe keeps expanding, a quiet push that ensures nothing stays together forever on the largest scales. Some structures hold on because gravity is stronger up close, but in the end, expansion will have the final word. When you look up at the stars tonight, you're seeing this story in motion. The faint smudge of Andromeda is a glimpse into the future. It's already on its way to meet us, and in the time scale of galaxies, that meeting is just around the corner. It's one more reminder that the universe is never truly still. Even when things seem frozen, they are drifting, merging, and slowly, inevitably, moving toward a future where all the lights will go out. For now, though, we live in the brief age of brilliant skies, the moment when galaxies still shine, when the Milky Way still arcs above you, when the stars still fill the darkness with stories of what came before and what's yet to come. Over the billions of years to come, the merging of galaxies will play out again and again, wherever gravity is strong enough to keep pulling stars together. But these mergers are only part of the bigger picture. At the same time, the universe's expansion continues its slow work, spreading matter thinner, cooling energy, and making new star formation harder and harder. The galaxies that do merge will spend their remaining gas making new stars, but even that fuel will run out. When that happens, the galaxies will be filled with old, dying stars and the remnants they leave behind: white dwarfs, neutron stars, and black holes. New stars will become increasingly rare until, one day, they stop forming altogether. Star formation is possible because clouds of gas and dust can collapse under gravity, but the raw material for new stars is not infinite. Each generation of stars uses up hydrogen, the simplest and most abundant element, to make heavier elements. Some gas gets locked away forever inside stellar remnants or planets. Some is blown out into space by stellar winds or supernova explosions, but not all of it will be recycled into new stars. Astronomers estimate that in about 100 trillion years, the last new stars will flicker into life. These final stars will likely be red dwarfs, the smallest, dimmest, and longest living type of star. Red dwarfs burn their fuel so slowly that they can shine for trillions of years, far longer than stars like our sun. But even they cannot shine forever. When their hydrogen is gone, they too will fade. When the last red dwarf exhausts its fuel, the universe will enter a time that some scientists call the degenerate era, an era ruled not by bright stars, but by what stars leave behind. The darkness will not come all at once. Instead, the sky will grow darker as each star reaches its end. The final lights will be the faint, fading glow of the last white dwarfs slowly cooling toward darkness. It's a strange future to imagine. A universe that began in a blaze of light and energy, now drifting in silence. Its once bright galaxies reduced to collections of cold, dark remnants. In this time, collisions between remnants can still happen. Sometimes two white dwarfs might merge and create a new explosion. Neutron stars might crash together, briefly flaring before settling back into darkness. But these events will become rarer and rarer as distances grow and fuel disappears. Meanwhile, black holes will continue to feed on any matter that wanders too close. A stray star, a rogue planet, or gas clouds pulled by gravity. These giants will hold on to the last bits of mass and energy for as long as they can. But even they are not immune to the rules of physics that pull everything toward a final stillness. When you think about the end of star formation, it helps to remember just how long this process takes. 100 trillion years is so far beyond human experience that it's almost impossible to picture. But time in the universe does not rush. It moves steadily, patiently. In our brief moment here, the sky above is still bright with stars. The Milky Way still spirals. Andromeda still glows on the horizon. It is all temporary, but temporary on a time scale so vast that our lives feel like flickers by comparison. Even as new stars fade away, the universe will not be empty. The remnants that remain will keep drifting through space, colliding, merging, and sometimes flaring back to life in small, quiet ways. But the big show, the era of star birth and blazing light, will be over. If you step back and look at this long timeline, you see how each stage of the universe builds on the last. The birth of stars brought light and complexity. Their deaths scattered the elements needed for planets and life. The slow end of star formation is simply the final step in a process that began with the Big Bang, a gradual winding down, not with an explosion, but with a long, deep silence. When you look up at the night sky tonight, you are seeing this story in progress. You live in a rare age, when stars still shine and galaxies still light up the darkness. One day, that light will be gone. But for now, it's here for you to see. A reminder that every moment of warmth, every ray of starlight, is part of something that once began and will someday end. As the last stars go out and galaxies stop making new ones, the universe will shift into an era ruled by black holes. These strange objects, born from the deaths of massive stars and the mergers of galaxies, will be the last major cosmic structures left standing. For ages, black holes were thought to be the universe's final destination for matter. Anything that crossed the event horizon would be trapped forever, lost to the outside universe. But Stephen Hawking showed that black holes do not last forever. Through a process now called Hawking radiation, they can lose tiny amounts of mass over time. This happens because of quantum effects near the event horizon. Virtual particles pop in and out of existence everywhere in space. Near a black hole's edge, one of these particles might fall in while the other escapes. To an outside observer, it looks like the black hole is radiating energy. Over mind-boggling lengths of time, this process causes the black hole to shrink, little by little. The time scale for this evaporation is almost beyond comprehension. A black hole with the mass of our sun would take 10 to evaporate completely. That's a 1 followed by 67 zeros. A stretch of time so vast that even the entire current age of the universe is like an instant by comparison. The supermassive black holes that sit at the centers of galaxies will last even longer, perhaps as long as 10 to 100 years. But eventually, they too will lose mass and vanish, releasing the last bits of trapped energy back into the universe. When the final black hole evaporates, the universe will reach what scientists call heat death. It's not an explosion or collapse, but the ultimate end state of a cosmos that has used up all its usable energy. The universe will be maximally disordered, full of thin, cold radiation and a few drifting subatomic particles that almost never meet. With no energy differences left, no new structures can form, and nothing meaningful can happen. This idea sounds grim at first. A cosmos where all motion, heat, and life fade into an endless, quiet darkness. But there is also something peaceful about it. The same laws of physics that gave birth to stars, galaxies, and life are the ones that ensure it all winds down gently, step by step. In this final era, the universe will keep expanding. Space will grow so vast that the remaining particles and photons will rarely, if ever, interact. Any warmth left will be spread so thin that it can't clump or ignite anything new. Time itself won't stop, but with nothing left to mark its passage, it will feel like silence stretched to infinity. Some physicists wonder if this is truly the final word. Could something unexpected happen? Could new physics appear at these extreme timescales? Could the universe find a way to renew itself? There are ideas: the Big Crunch, the Big Rip, or cosmic bounces. But right now, the best evidence says the slow heat death is the most likely path. If that's true, then the universe's story is one of gradual change, from a blazing birth to a patient unwinding. It is not dramatic, but calm, not sudden, but stretched out over incomprehensible spans of time. And you, here and now, are part of that same timeline, alive during a brief, brilliant moment when stars shine, galaxies glow, and black holes still quietly feed in the darkness. You are a witness to a phase that will one day be gone, but for now, it is here to light your nights and guide your thoughts. When you lie back and drift toward sleep, you can let this idea settle gently in your mind. The universe has always been moving toward stillness, but the stillness takes so long that every moment you experience is a precious, temporary spark in the dark. The heat death will come one day, not with a bang, but with a whisper. And in the meantime, the story goes on. One drifting star, one glowing galaxy at a time. The idea of heat death, this endless drift toward silence and cold, is the scenario that most cosmologists think is likely. But it's not the only possibility people have imagined. Over the years, scientists have tested other ideas, using observations and mathematics to see what else the distant future might hold. One alternative was once called the Big Crunch. In this version, the expansion of the universe would someday slow down, stop, and then reverse. Galaxies would start moving closer together instead of drifting apart. Over billions of years, everything would collapse inward. Galaxies would merge, stars would crash into each other, and temperatures would rise as matter and energy squeezed tighter and tighter. Eventually, everything would collapse into an incredibly dense, hot state, a sort of mirror image of the Big Bang. Some early models of the universe made this idea seem reasonable. If the average density of matter was high enough, gravity might be able to stop expansion and pull everything back. But when astronomers started measuring distant supernovae and the cosmic microwave background in more detail, the data told a different story. The universe isn't slowing down, it's expanding faster. Dark energy, whatever it really is, seems to push everything apart. The Big Crunch became less and less likely. Another possibility is called the Big Rip. This idea comes from the same mysterious dark energy that speeds up the expansion. If dark energy's strength changes over time, growing instead of staying constant, then the expansion could become so powerful that it tears apart everything, even at the smallest scales. In this scenario, galaxies would be pulled apart, then star systems, then planets. In the final moments, even atoms could be ripped apart by expansion faster than the forces that hold them together. For the Big Rip to happen, dark energy would need to act differently than we see today. So far, observations suggest that dark energy is constant, behaving like Einstein's cosmological constant. If it stays that way, a Big Rip is unlikely. But the possibility shows how much we still don't understand about this invisible force that shapes the fate of the universe. A third idea, less discussed but fascinating, is the idea of cosmic rebirths, universes that bounce. Some theories suggest that instead of ending in heat death or a big crunch, the universe could go through cycles. After collapsing into a dense state, it could bounce back in a new Big Bang, starting the process all over again. These ideas often connect to theories about quantum gravity or extra dimensions, which might prevent the universe from truly reaching a point of infinite density. There is no clear evidence for a cosmic bounce, but it shows how the universe's future is tied to the deepest questions about space, time, and matter. Understanding what dark energy is, whether it changes, and how it behaves at extreme scales could reshape our picture of what the end even means. Meanwhile, physicists continue to test these ideas. They measure how galaxies move, how the cosmic microwave background looks, and whether subtle patterns in large-scale structures match predictions. Each new piece of data helps narrow down what's likely and what's possible only in our imaginations. What all these scenarios share is a sense that the universe changes slowly. Whether it ends in a quiet heat death, a sudden tear, or an endless cycle of rebirth, the scales of time involved are beyond anything we experience in our daily lives. It's easy to think of the universe as eternal, unchanging. When you look up at the stars tonight, they feel timeless. But science shows us they are not. They were born from gas and gravity. They shine by fusing elements, and they will end when their fuel runs out. The same is true for the largest structures, the galaxies, clusters, and filaments that weave through space. All of them live according to the same physical laws. Knowing that doesn't make the present less meaningful. In fact, it makes every moment more precious. You live during a rare time when the universe is still bright with stars, when the night sky still holds galaxies close enough to see, when life is possible in at least one small corner of it all. So whether the universe fades gently, tears itself apart, or bounces back in a new beginning, the truth is that your place is here now, at a crossroads in cosmic time when you can look up and wonder how it all might end. And while these questions are big, they don't have to keep you awake. They can be reminders that change happens on scales so vast that they feel almost still. In the end, the universe's distant fate is written in laws that also make each sunrise, each starlit night, and each heartbeat possible. As you think about how the universe might end, another question often comes up. What does it mean for us? Does any of this change how we live our daily lives? In some ways, knowing about heat death, black holes evaporating, or galaxies drifting apart doesn't affect your morning coffee, your walk in the park, or the people you love. The ending is so far away that it has no practical effect on the choices you make tomorrow. Yet many people find that it changes how they see themselves and the world. Learning that the universe will eventually fade into darkness can make you feel small. It shows just how brief human life is compared to the lifetime of stars or the age of galaxies. Civilizations rise and fall in the blink of an eye on a cosmic clock. But feeling small doesn't have to be sad. It can be humbling, a reminder that you're part of something enormous and old, something that will go on long after you're gone. Some people find comfort in this. The same physical laws that bring about the end also allow stars to shine, planets to form, and life to exist at all. Those laws created the conditions for you to think, to feel, to wonder about the universe. If the universe were different, maybe you wouldn't be here to ask these questions. This perspective can help you see life's ordinary moments in a new light. The warmth of sunlight on your skin is ancient energy, a chain reaction that began deep in the sun's core millions of years ago. The iron in your blood came from a star that died billions of years ago. Even the air you breathe is shaped by the history of stars that lived and died long before our planet was formed. Knowing this doesn't take away from daily life. It adds to it. You can look at the stars and understand that they are your distant relatives. You can see yourself as a tiny piece of a story that began at the Big Bang and continues long into the future. It can also remind you that meaning doesn't come from how long something lasts, but from what you do with the time you have. Stars shine until they can't, and then they leave behind the elements for something new. Maybe people are like that too. Our actions, our connections, the love and care we share. These are the things that echo forward, even when we're gone. So, does knowing the universe will end change anything? Maybe not the tasks on your to-do list or the meals you'll cook tomorrow, but it can shape how you see your place in the world. You are not separate from the universe. You are made of the same atoms that drifted through space for billions of years before becoming you. This doesn't mean everything is predetermined. It means you exist in a moment when the universe is bright, warm, and full of possibility. You have a chance to notice the stars before they fade, to feel the warmth of the sun before it swells into a red giant, to share stories, ideas, and questions before they drift away. Some people find a sense of freedom in this knowledge. The ending is so far away that it removes pressure. You can live your life fully knowing that it is your moment to be alive, to wonder, to rest under a sky full of ancient light. And when you drift off to sleep tonight, you can carry that calm with you, the simple truth that while the universe will change, for now, you are here. You are a witness to a cosmos that still holds warmth and starlight, a small piece of an immense story still unfolding, one heartbeat and one breath at a time. The heat death is the scenario most scientists consider likely, but when you look deeply into the physics of the universe, other possible endings appear. These possibilities are more than just science fiction. They come from real attempts to understand the nature of space, time, energy, and the hidden parts of reality we don't yet fully grasp. One alternative that once seemed promising is the idea of the Big Crunch. In this version of the universe, gravity eventually overcomes expansion. After billions or trillions of years of drifting apart, galaxies would begin to slow down, stop, and then reverse course. Space itself would start to contract, pulling everything closer together. Galaxies would merge, then collide more often, until eventually, all matter and energy collapse into an ultra-dense, hot state. In some ways, this would mirror the conditions of the Big Bang, the universe ending as it began. For the Big Crunch to happen, the universe would need to contain enough matter to make gravity stronger than the force driving expansion. Astronomers used to debate whether there was enough matter for this to be possible, but measurements of how galaxies move and how light bends around clusters showed there simply isn't enough mass. Dark energy's push appears stronger than gravity's pull on cosmic scales, which means the expansion is not slowing down, it's speeding up. The Big Crunch, as far as current evidence shows, is unlikely. Another idea is the Big Rip, which suggests an ending far more dramatic than heat death. This scenario depends on what dark energy really is and how it behaves over time. If dark energy grows stronger, it could push the universe apart with increasing force. At first, this would just keep galaxies drifting away faster and faster. But over time, the expansion could start to pull apart galaxy clusters, then individual galaxies, then star systems. If this process continues, the force of expansion would eventually become so strong that it would overcome the gravity holding planets in orbit, the forces that hold matter together, and even the forces binding atoms themselves. In the final moments, everything, stars, planets, molecules, atoms, would be torn apart. This is the Big Rip. The idea that space itself could shred all matter down to its smallest pieces. But so far, observations suggest that dark energy acts like a constant force, not an increasing one. So the Big Rip is more of a thought experiment than an expected outcome. There are also ideas about cosmic rebirth, scenarios in which the universe doesn't just drift into silence, but finds a way to renew itself. Some theories suggest that instead of collapsing into a big crunch, the universe could bounce. In these bouncing models, the universe might contract into a dense state, then rebound in a new Big Bang, starting everything over again. This idea ties into some approaches to quantum gravity, where extreme densities prevent a singularity by creating a repulsive force that reverses the collapse. So far, there's no direct evidence for a bounce. But these ideas remind us that the rules we know might not cover every extreme situation. The physics at the smallest scales, the realm of quantum mechanics, doesn't always agree with the physics of the largest scales, general relativity. This gap leaves room for surprises, especially in the extreme conditions at the beginning or end of a universe. Another speculative idea is that black holes could become seeds for new universes. Some theorists have proposed that when matter collapses into a black hole, it could create a pocket universe that pinches off from our own, like a bubble budding from a larger bubble. In this view, every black hole might be a gateway to a new cosmos. This idea is hard to test and sits on the edge of what science can currently explore. Then there's the multiverse concept, the idea that our universe is just one of countless others, each with its own laws of physics. In some versions, new universes constantly bud off from regions where space inflates eternally. In others, each black hole becomes a separate universe with slightly different physical constants. If any of these ideas are true, the end of our universe wouldn't be the end of everything, just the closing of one chapter in a much larger cosmic story. None of these possibilities change how our universe appears to be evolving right now. Expansion continues. Stars burn their fuel. Black holes gather mass. Over unimaginable timescales, energy spreads thinner. Whether it all ends in silence, a collapse, a tear, or a bounce depends on factors we still don't fully understand, especially dark energy, the invisible force that makes up most of the universe's energy content. For now, the evidence leans strongly toward an endless expansion that leads to heat death, a universe drifting ever outward until it becomes cold, dark, and quiet. Other endings are reminders that the universe is still full of mysteries, gaps in our knowledge that keep scientists searching, testing, and wondering. This is part of what makes the story so human. Even when we think we understand how everything will unfold, we keep asking questions. We build better instruments, gather more data, and test our theories against what the universe shows us. The fact that we can do this, that beings made of stardust can imagine the universe's ending and try to test it, is remarkable on its own. So when you lie back tonight, you don't need to decide whether you believe in a big crunch, a big rip, or endless silence. You can hold them all in your mind like possibilities drifting across an infinite sky, reminders that the story of the cosmos is still being written, one quiet discovery at a time. If you followed this slow journey from the birth of stars to the fading of the last black holes, you might still find yourself wondering, what does all this mean for us, here and now? In daily life, these grand time scales are so distant, they almost feel imaginary. The idea that stars will stop forming, that galaxies will drift apart beyond view, or that black holes will eventually vanish, doesn't affect what you'll do tomorrow morning. You'll still wake up, make coffee, send messages, see the people you love. The universe's distant fate doesn't rewrite your plans. But it does offer a perspective that can quietly change how you see your life. It can remind you how fleeting everything is. Not in a sad way, but in a way that makes ordinary moments feel more meaningful. Knowing that the stars will one day burn out can make their light tonight feel like a rare gift. For some people, this knowledge sparks a sense of humility. We live on a small planet, orbiting an average star in one galaxy among billions. Our entire human story fits into a tiny slice of cosmic time. Our oldest ancestors looked at the same night sky we do, though they couldn't yet know how stars are born, live, and die. Now, in just a few centuries of science, we've pieced together clues that show us the universe is changing, always changing, from the tiniest particles to the largest structures. This perspective doesn't mean that human life is pointless. If anything, it shows how remarkable it is that we're here at all. The atoms that make up your body were forged in the hearts of stars that exploded long before Earth existed. Every breath you take includes oxygen that comes from stars that burned their fuel billions of years ago. Your thoughts, even the ones you're having right now as you listen, are built from particles that drifted through space before gathering into this moment. The universe's far future also reminds us that nothing lasts forever. Empires rise and fall, species appear and vanish, stars flare to life and burn out. But what we do now, the stories we tell, the care we give, the memories we pass on, these things echo through time in ways we can't always see. You don't have to change the course of galaxies to leave an imprint. Maybe it's enough to know that your life is your piece of the cosmic story, a moment of warmth, thought, and feeling in a universe that will one day be cold and still. For some people, the idea that the universe will end makes them wonder about meaning itself. But meaning isn't something handed down from the stars. It's something people create. It lives in the bonds we share, the ideas we explore, the moments of wonder when we look at a sky full of light and think about how it all came to be. Knowing how the universe will end doesn't take away the beauty of a sunrise, the hush of falling snow, or the warmth of holding someone's hand. It makes those moments feel even more precious. They are short, yes, but they are real. Your tiny place in a cosmic timeline that stretches far beyond what you can see. As you settle deeper into sleep tonight, you can let this idea rest with you. The universe is changing all the time, but for now, you're here. Stars are still shining. Galaxies are still drifting. The warmth of the sun still reaches you. You are part of it all, made from it all. And when your thoughts wander to distant futures, you can return to this moment, breathing slowly, resting, alive in the brief, bright now. The story of how the universe will end is really a story about how everything slows down, spreads out, and fades into quiet. But in this story, the final moments never come all at once. They arrive so slowly that even the idea of an ending almost loses its meaning. In the far future, when the last black holes have evaporated and the last white dwarfs have cooled into black dwarfs, what remains is a universe drifting through the deepest quiet you can imagine. Space will keep expanding, carrying the last scattered particles farther and farther apart. In this darkness, there is no more fuel to ignite new stars, no gas clouds to gather and collapse, no galaxies left to collide and stir up new bursts of light. The energy that once formed galaxies, stars, and planets is still there, but it has spread so thin that nothing new can happen. This is the state physicists call heat death, the moment when the universe has reached maximum entropy and everything is evenly spread out, cold and still. Some remnants of what once was will linger. Particles like electrons and neutrinos will drift endlessly, so far apart that they rarely, if ever, interact. Occasional collisions might still happen, but the odds are so low that you could wait for longer than the entire age of the universe and never see one. In this far-off era, time itself won't stop. It will stretch on and on, but with no more structure, no more energy differences, no more surprises. The passage of time will be marked only by the endless drift of particles through an ocean of space that has grown too vast for them to find each other. It's a strange thing to imagine. We're used to thinking of the universe as full of events, stars flaring to life, galaxies spinning, black holes colliding. Our daily lives are marked by change, seasons, days, hours. But in this final era, change slows to almost nothing. The universe becomes a place where nothing new is born and nothing old is left to fade. It is as if the clock is still ticking, but there is nothing left for it to measure. Does that mean the universe truly ends? Not in the sense of something dramatic. There is no final explosion, no last burst of light. Instead, the universe falls quiet, a kind of cosmic twilight that never quite reaches darkness because the faintest traces of energy and motion still exist, drifting endlessly. In that vast silence, the echoes of what came before will still be there, written into the particles themselves. Every atom, every faint wave of energy is a relic of stars that once burned, of galaxies that once collided, of black holes that once fed on gas and light. It's all still there, just spread out so thin that it can never be gathered up again. Some thinkers find this vision unsettling, a lonely, cold future where nothing happens. But there is also something peaceful about it. The universe doesn't crash or burn out in an instant. It simply unwinds, step by patient step, until its energy is spent. The same laws of physics that created brilliant bursts of light and warmth guide it to this quiet resting place. And when you think about this final quiet, it can remind you how unique this moment is right now. We live in what some scientists call the stelliferous era, the age of stars. This is the time when the universe is bright and full of warmth, when galaxies still glitter, when planets still orbit suns, when life can exist. Compared to the long, dark future that awaits, this age is like a single bright day that shines before a long night. For now, you are alive in this day. The sun rises and sets. The Milky Way stretches across the sky. You can sit by a window and feel the warmth of sunlight on your face. You can look up at stars that formed long before you were born and will keep shining long after you're gone. When you lie down at night, you rest under a sky that is still telling its story. A sky that remembers what came before and hints at what comes next. The ancient starlight that touches your eyes tonight has traveled for years, centuries, even millennia to find you. That light is part of you now, a reminder that you are connected to the stars not just by imagination, but by the same particles and forces that shape everything. One day, the stars will go out. One day, the galaxies will drift beyond view. One day, The last black holes will vanish with a whisper of hawking radiation. But that day is so far away that it barely matters for you tonight. It is comforting, in a way, to know that the universe takes its time. And it's humbling to remember that you are here for this brief, warm window. A tiny spark of thought, breath, and wonder in a universe that will one day fall quiet. That spark is yours. You carry it every day in every small act of curiosity, kindness, and care. When the silence comes, it will come gently. And until then, the story goes on. It flows through the stars above, through the warmth of the sun, through the atoms that drifted across the universe to become you. So as you drift toward sleep, let that story rest with you. The universe moves slowly toward stillness, but for now, it is alive with light, warmth, and possibility. You are part of that, a moment of life in a cosmos that remembers, fades, and waits. And tonight, that is enough.